Welcome back, everybody, for another deep dive. This time, we're going to be taking a look at the world of AI,
Oh, yeah.
specifically how these models can learn and remember over long periods.
Okay.
And you know what's awesome? A listener actually sent us in a research paper called Titans, Learning to Memorize at Test Time.
Nice.
And I got to tell you, I was hooked immediately by the title.
Mm-hmm.
But what really blew me away was how this paper draws parallels between AI learning and the way that our own brains work.
Yeah, is a fascinating approach.
Yeah.
And the paper challenges the idea that we need to, cram all the knowledge into a model during its initial training phase.
Okay, so instead of like force feeding the AI everything at once, Titans learn to remember things on the fly.
Exactly.
That's pretty different from how we usually think about AI, right?
Yeah, exactly. The paper actually points out that a lot of popular AI models,
Mm-hmm.
like transformers, they're great at understanding immediate relationships,
Mm.
like analyzing a sentence or a paragraph,
Mhm.
but they really struggle when they need to remember information from way back.
So they have something like a short-term memory, but not a great long-term memory.
That's a great way to put it.
Okay.
And that limitation is what the Titans model really tries to overcome.
Yeah.
The research focuses on equipping AI with both short-term and long-term memory, just like us.
So how do these Titans actually do that? Like, do they just store every single detail that they encounter?
Well, that's where it gets really clever.
Okay.
Titans actually learn to memorize at test time,
Mm-hmm.
meaning they figure out what's important to remember as they encounter new information.
Okay.
Instead of memorizing everything, they prioritize the things that are most surprising or unexpected based on what they've already learned.
That's interesting. So they're like little detectives constantly looking for clues that don't fit the pattern.
Yeah.
So how does this surprise-based memory actually help them perform better?
Well, think about it this way.
Okay.
If you were trying to learn a new language,
Mhm.
which words would you remember better? The common ones that you hear all the time, or the ones that sound unusual or have, unique meanings.
Probably the unusual ones just because they stand out. But
Exactly.
wouldn't a model that only remembers surprises miss out on important information that's not necessarily unexpected?
That's a great question.
Yeah.
And the researchers actually address that concern by combining the surprise-based long-term memory with a more traditional short-term memory.
Okay.
That way, the model retains the ability to process and understand all the information that it encounters
Mm-hmm.
while also flagging the most important or unusual details for long-term storage.
So it's like having two memory systems working together.
Yeah.
One that handles the day-to-day information and another that acts like a highlighter,
Right.
marking the most crucial points.
Exactly.
But we're talking about AI here, so how do they actually build this long-term memory?
Mhm.
Is it like a giant storage drive packed with data?
Not exactly. The long-term memory is actually stored within the parameters of a deep neural network.
Okay, I'm already sensing this might get a bit technical,
Mm-hmm.
but our listeners trust us to break it down, so let's do it.
Right.
What's a deep neural network, and how does it act like a memory?
Okay. So imagine a network of interconnected nodes,
Okay.
kind of like a complex web.
Uh-huh.
Each connection in this web has a certain strength or weight,
Okay.
and these weights represent the model's memory.
Mm-hmm.
As the model learns, these connections are constantly being adjusted, strengthening some and weakening others.
So it's not just storing raw data, it's learning and adapting the connections based on its experiences.
Right.
That sounds a lot more like how our brains work, right?
Exactly.
But how do those weights actually translate into remembering specific information?
So think of it like this. Each node in the network represents a concept or an idea,
Okay.
and the connections between these nodes represent the relationships between those concepts.
So the stronger the connection between two nodes, the more closely those concepts are linked in the model's memory.
Precisely.
Okay.
And as the model encounters new information, it adjusts the strengths of these connections,
Mm-hmm.
effectively rewiring its memory to reflect its evolving understanding of the world.
So it's like building a mental map where the landmarks are concepts and the roads connecting them are the relationships the model has learned.
That's a great way to put it.
That's really cool. This whole process, it sounds pretty computationally intensive, though.
Right.
How do Titans manage to do all this without requiring like massive amounts of processing power?
Yeah, that's another really clever aspect of their design.
Okay.
They actually use a technique similar to gradient descent with momentum.
Okay.
which is a concept often used in optimization algorithms.
Gradient descent with momentum.
Yeah.
I gotta admit, that sounds a bit intimidating.
It is a mouthful.
Yeah.
Can you break it down for us non-AI experts? Sure. Imagine you're rolling a ball down a hill.
Okay.
The steeper the hill, the faster the ball gains momentum, right?
Yeah.
In this analogy, the steepness of the hill represents how surprising a piece of information is to the model.
Okay.
The more surprising the information, the more momentum the learning process gains.
Uh-huh.
And that leads to faster and more efficient memory formation.
So the more surprised the model is, the more effort it puts into remembering that information.
Exactly.
That's kind of like when you hear a juicy piece of gossip, you just can't help but commit it to memory.
That's a great way to put it, yeah.
Yeah. And just like our memories fade over time, Titans also have a built-in forgetting mechanism.
Right.
This helps them manage their memory capacity and prioritize what's truly important.
Exactly.
So they're not just mindless data hoarders. They're actually curating their memories, choosing which details to keep and which to let go.
Yeah.
I'm guessing this forgetting mechanism is really important for preventing them from getting bogged down with irrelevant information.
Precisely. And it's actually designed to be adaptive,
Oh.
meaning it adjusts how quickly information is forgotten based on its relevance.
So it's constantly reevaluating what it needs to hold on to.
Right.
That's pretty cool.
Yeah.
Okay, so we've talked about how Titans store their long-term memories, but how do they actually access and use this information when they need it?
Right.
It can't be easy to search through a giant network of interconnected nodes, right?
You're right. Simply searching through that whole network would be incredibly inefficient.
Yeah.
So that's where attention comes in again.
Okay.
Remember how we talked about attention being like the model's short-term memory?
Yeah, it's what allows them to focus on the most relevant information in a given context.
Exactly. When Titans need to access their long-term memory, they actually use attention to guide their search,
Oh, yeah.
focusing on the parts of the network that are most likely to contain relevant information.
So it's like having a mental spotlight that helps them zero in on the most important memories.
That's a great analogy. Now let's shift gears a bit and talk about how this whole long-term memory system actually improves the performance of Titans.
Okay.
One of the key advantages is their ability to handle long sequences of information much better than traditional models.
We talked earlier about how models like transformers struggle with long sequences because their short-term memory gets overloaded.
Right.
Are you saying that Titans can overcome this limitation because of their long-term memory?
That's exactly right.
Okay.
By storing important information in their long-term memory, Titans can just free up their short-term memory to focus on the immediate context.
Okay.
This allows them to process much longer sequences without losing track of the overall narrative.
It's like having a separate notepad where you can jot down key points as you read a long article. That
Right.
way you don't have to keep everything in your head at once, and you can always refer back to your notes if you need a refresher.
Exactly. And another advantage of Titans is their ability to learn more complex, nonlinear relationships within the data. Traditional models often struggle with this because they rely on simpler, linear representations of information.
Can you give us an example of a nonlinear relationship? I'm having trouble picturing what that would look like in the context of AI.
Sure. Imagine you're trying to predict the stock market.
Okay.
There are countless factors that can influence stock prices.
Right.
And these factors interact in very complex ways. A simple linear model might try to find a straight line relationship between, say, interest rates and stock prices.
Okay.
But in reality, the relationship is much more nuanced and dynamic.
So a linear model would be like trying to fit a square peg into a round hole, while Titans can adapt to the complexities of the real world.
Exactly.
Okay.
By using deep neural networks for their long-term memory, Titans can capture these intricate nonlinear relationships much more effectively than traditional models.
So it's giving them a more flexible way of thinking about the world.
Right.
Okay, so Titans can handle long sequences and learn complex relationships. But how do those capabilities actually translate into real-world applications? Like, what kinds of problems can Titans solve that other models can't?
That's a great question.
Yeah.
And the paper highlights a few key areas where Titans excel.
Okay.
One of them is language modeling,
Okay.
which involves predicting the next word in a sequence based on the preceding words.
So like those autocomplete features that we see in text messaging and email.
Exactly.
Okay.
But language modeling actually goes beyond just suggesting the next word.
Okay.
It's about understanding the nuances of language, the relationships between words, and even the underlying meaning of a text.
And Titans are better at this than other models because they can remember more context.
Precisely.
Okay.
By accessing their long-term memory, Titans can take into account a much wider range of information when predicting the next word.
So it's like they're reading the entire book, not just the last few pages.
Yeah.
That must make a huge difference in their ability to understand the subtle nuances of language. Okay, cool. So we've got language modeling.
Hmm.
Another area where Titans shine is common sense reasoning.
Right.
And this involves making inferences about the world based on our everyday knowledge and experiences.
Exactly. So, knowing that if someone is holding an umbrella, it's probably raining outside.
Right.
These kinds of inferences might seem simple to us,
Mm-hmm.
but they're actually quite challenging for AI models.
Because they don't have the same kind of lived experience that we do.
Right. Traditional models often struggle with common sense reasoning because they lack a robust, long-term memory
Okay.
to store and access this kind of knowledge.
But Titans can draw on their long-term memory to make those connections. It's like they've been trained on a massive data set of everyday experiences.
That's a great way to think about it.
Yeah.
And this ability to reason about the world in a more human-like way makes Titans particularly well-suited for tasks that require understanding context, making inferences, and even predicting future events.
Wow. So we've got language modeling and common sense reasoning. Hmm.
What other areas do Titans excel in?
The paper also highlights their performance on what's known as the needle in a haystack problem.
Okay.
This involves finding a specific piece of information buried within a massive amount of data.
So like trying to find a particular quote in a giant library.
Exactly.
Okay.
And Titans have shown a remarkable ability to solve this kind of problem, even outperforming models with significantly more parameters.
Wait, more parameters usually means a more powerful model,
Yeah,
right? So Titans are achieving better results with fewer resources.
it is.
That's pretty impressive.
And this highlights the importance of having the right kind of architecture and learning mechanisms.
Right.
It's not just about brute force computation. It's
Mhm.
about efficiency and intelligent use of resources.
Okay, so we've covered a lot of ground here.
Yeah, we have.
We've talked about how Titans store their memories, how they access and use this information, and how these capabilities translate into real-world applications.
But the paper also mentions different variations of the Titan model, right? It's not just a one-size-fits-all approach.
You're right. The researchers actually present 3 different Titan architecture variants,
Okay.
each offering a slightly different way to incorporate long-term memory.
That's fascinating. So it's like they've created a toolkit for building AI models with long-term memory.
Mm-hmm.
And each variant is like a different tool for different jobs.
Exactly. Let's dive into these variants and explore how they differ in their approach to long-term memory.
All right, so let's break down these different Titan variants.
Sure.
What are we looking at here?
So the first variant is called memory as a context,
Right.
or MA.
Okay.
It's all about using the long-term memory to provide context for the current information that the model is processing.
So it's like having a mental cheat sheet that the model can refer to whenever it encounters something new.
That's a great way to put it.
Okay.
Imagine you're reading a mystery novel
Mm-hmm.
and you come across a clue. You might flip back a few pages to refresh your memory on the details of a previous scene.
Yeah.
That's essentially what MNC does.
Okay.
It takes the current input, breaks it down into segments, and then queries its long-term memory for any relevant information from previous segments.
So it's constantly connecting the dots between past and present information.
Right.
That sounds like a pretty effective way to build a coherent understanding of a complex narrative.
Exactly.
Okay.
And the attention mechanism, which remember acts like the model's short-term memory, plays a key role in this process.
Uh-huh.
It helps decide which pieces of information from the long-term memory are actually relevant to the current context.
So it's not just blindly dumping everything from its memory bank.
Mhm.
It's selectively choosing the most useful bits based on the current situation.
Exactly.
Okay, so MSC is all about using memory as a source of context.
Yeah.
What about the next variant?
The second variant is called memory as a gate, or MAG.
Mhm.
This one takes a different approach, using the long-term memory to control the flow of information within the model.
So instead of providing context, it's acting more like a filter.
Exactly. Think of it like a gatekeeper that decides which information gets through and which gets blocked.
Hmm.
It works in conjunction with a sliding window attention mechanism, which we've already talked about as a kind of short-term memory.
Right, right. So we've got two memory systems working together.
Yeah.
The short-term memory focusing on the immediate context and the long-term memory acting as a gatekeeper
Right.
to control the overall flow of information.
Exactly. And the key to this approach is the gating mechanism,
Okay.
which determines how much weight or importance to give to the information coming from each memory system.
So it's like having a volume knob that can adjust the balance between short-term and long-term memory depending on the situation.
That's a great analogy.
All right, and the last one.
The final variant is memory as a layer,
Hmm.
or
Yeah.
MAL. This one takes a more integrated approach, weaving the long-term memory directly into the layers of the neural network.
So instead of being a separate module, the memory becomes an integral part of the model's thinking process.
Precisely.
Okay.
It's like building a house where the foundation itself is made of memories.
I like that.
This approach is often used in hybrid models that combine recurrent networks with attention mechanisms.
That's interesting to see how each of these variants takes a different approach to incorporating long-term memory into AI models.
Yeah,
They're like different flavors of the same recipe, each with its own unique twist.
exactly.
So, did the researchers find that one of these was kind of the best, or is it really just dependent on the problem you're trying to solve?
The researchers actually found that each variant has its own strengths and weaknesses depending on the specific task at hand.
Makes sense.
But the key takeaway is that they all demonstrate the power and potential of long-term memory in AI.
It's amazing to think that we're now able to create AI that can learn and remember in ways that were once thought to be exclusively human capabilities.
It really highlights how AI research is constantly pushing the boundaries of what's possible.
Yeah.
And by drawing inspiration from the human brain, we're creating AI that's not just more powerful, but also more adaptable and intelligent.
This has been a truly fascinating deep dive into the world of AI and long-term memory.
Yeah,
We've explored the inner workings of the Titans model, unpacked its different variants, and even touched on the potential impact this research could have on the future of AI.
It's clear that this is just the beginning of a very exciting journey.
Yeah.
As we continue to explore the intersection of AI and human cognition, we can expect even more groundbreaking discoveries in the years to come.
And who knows, maybe one day we'll have AI that can not only learn and remember like humans, but also dream, imagine, and even feel emotions.
That's a thought-provoking idea.
Now that's something to ponder.
It certainly is.
That's it for our deep dive today. Until next time, keep exploring, keep learning, and keep those synapses firing.